Hello, I'm Mr. Rose, and today we're going to talk about energy and conservation of energy. So just to get us all on the same page, we want to talk about a couple of vocabulary things. First, potential energy. Potential energy is just going to be our general expression for a configuration of objects. We also today are going to expand our thinking from our work kinetic energy theorem to just a general work energy theorem. For example, if I take a ball and I throw that ball up in the air, we know that work has to be done on that ball in two different respects. One is I take that ball and I throw the ball up. We know the ball is moving up into the air against the force of gravity, so we can say that the work done by gravity is negative. When the ball falls back down, we can say that the work done by gravity is positive. What that means is we're going to have a new type of expression. We're going to say the change in work is equal to, the change in potential energy is equal to the negative work. And that doesn't actually matter if the ball is rising or if the ball is falling based on those negatives. A couple of things to remember. Number one, when we talk about a system is always going to be two or more objects. We can't talk about energy or the energy of an object if there's nothing to compare it to. Number two, we're going to say that when a force acts between an object and the rest of the system. So if I'm lifting an object up, there are two different things in that thing. It's the object and the Earth, say, system, if I'm talking about potential energy. Then 3 and 4 here are really a big to-do with conservation of energy. Basically, what 3 and 4 are going to say is in order for a change in the configuration of any system to happen, we need to imply some type of work. I need to do work to change that system. Like, if I'm compressing that spring, I am doing work into the system to change the system. Then, when the spring hits back, it is reversing the system. In other words, I gave that spring a whole lot of energy. When the spring throws that object back up into the air, it's changing the configuration in the opposite direction. So we're changing the direction of our work. Basically, we can say two things, that under perfect conditions, in other words, if we have a conservative force, the energy that I put in has to be the energy that I put out. In other words, work 1 is equal to negative work 2. If there is a non-conservative force, something like friction, we know those two things aren't the same anymore. I can't say that the work in is equal to the work out because we gave some energy to that system. In other words, I heated up objects, say, with thermal energy. So to continue, we can show this kind of simply. We're going to show that work and energy are relatively the same. It actually, again, doesn't really matter the type of work we're dealing with. And we're going to show that it's path independent. So if we go back to our expression from last chapter, work is equal to the integral of f of x dx. So I'm going to sum up all of those little parts as I apply a force to that object over some distance. If I know that my change in potential energy is negative work, then I can make a simple substitution and say that my change in potential energy is negative f of x dx, which is just the same thing, except now I have a negative here. If I lift against gravity, so I take an object and I lift that object up into the air, then I'm going to say my potential energy is negative mg dy. I'm going in the y direction. I take out my constants from my initial to my final position, and I get what looks like our work function from earlier, except now it's a change in potential energy. I know my change in potential energy as I lift something up is mass times gravity times that change in height. So here I go back to this little picture I drew before, what we were talking about. As I increase that height, I'm doing work, the gravitational force is doing work against that object. It's going up and up and up and up and up. I'm increasing the potential energy of that object. And basically, I'm transferring energy from the system into that object. So now I have a maximum potential energy when the object is up in the air. As that object comes back down, now the object is giving energy back into the system. In other words, as the object falls, its potential energy is leaving. Its kinetic energy, we know, is increasing, or it's giving energy back into that system, moving positive work being done. We can make the same assumptions with spring energy. Again, I know work is equal to negative f of x dx. If I'm talking about elastic potential energy, that means I'm talking about the force involved in moving a spring. So here we just have a negative k times x, where k was our spring constant. So I make a substitution. My change of potential energy is pulled out my negative kx dx, pull out my constants, and I know my change in potential energy now after I do the calculus is my spring constant, 1/2 x squared minus 1/2 x initial squared. If my initial position is 0, I know that my equilibrium position, so to speak, I know that my potential energy is just 1/2 kx squared, or a function with respect to x. So this brings us to our really powerful conclusions of conservation of energy. I know that in an isolated system, and we can isolate that system, that and only under conservative forces, that the kinetic energy and the potential energy change, but the total energy remains the same. In other words, just like that object going up or going down, the work going in is equal to the work going out, or I can increase kinetic energy while decreasing potential energy, and vice versa. What that means is then the total mechanical energy all of the time is conserved. And I just have a transfer of energy from potential energy to kinetic energy between any 2 points in that system. That also means I don't need to consider the work it takes to get from point A to point B to point C. I'm only talking about the total energy. It's a very powerful idea. We can state it simply by saying, if what I'm saying is true, that the total mechanical energy of that system is all of the kinetic energy plus all of the potential energy, if that system is an isolated system under only conservative forces. So what we do with that is, I know that the change in kinetic energy is equal to work from our last chapter. I also know that the change in potential energy is equal to my negative work. That being said, I can make a simple substitution. Say my change in kinetic energy is equal to the negative change in work, which means my final and my initial kinetic energy subtracted from each other is equal to my final and my initial potential energy when subtracted from each other. I collect my finals and my initials, and I can show that the final kinetic energy and the final potential energy has to equal the initial kinetic energy and the initial potential energy. Again, it's a very simple but powerful expression because it'll show us that our total mechanical energy is equal to our change in potential energy plus our change in kinetic energy, and that tells us that the change in the total mechanical energy of the system, or the change in potential plus the change in kinetic, has to be equal to 0. Now, this is only with conservative forces. Under non-conservative forces, we just add a simple expression of Q. Q is what we use for heat. So if I'm increasing the thermal energy, so to speak, like with a non-conservative force like friction, that's energy I can't get back out of the system. So I know my total mechanical energy is all the energy we were talking about plus that heat energy. That's all I have for today. Until next time, I'm Mr. Rose. Please comment, like, and subscribe, and I'll see you then.